All right, I handed back your quizzes. We'll talk about that in a few minutes, but I try to give a detailed explanation on there, so if it doesn't make sense to you, especially after we discuss it, please let me know. We talk about it individually, but so we still want to finish talking about the shapes of molecules. So this simulation is nice because I can start with an individual atom, and I can add lone pairs, and I can add bonds, and I can see how the shape of the molecule is affected by that. So let's say I have a single bond, and then I add a triple bond. So before I do that, just to point out, anytime I've got only two atoms, it's always going to be linear, right? It's never going to be some other shape. Two atoms is always linear. So when I'm asking you to label the geometry for atoms, if it's only attached to one other atom, you don't have to worry about it. I'm only asking you to label the geometry for central atoms. Any atom that has more than one other atom attached. So if I put another atom on there, let's say I've got a single bond there, I want to add a triple bond. What will the geometry be? Should be linear. Right? Because that's two electron domains. One is a bond, a single bond, one is a triple bond, and they spread out to avoid repulsion. So the angle is 180. But when I've got two electron domains and no lone pairs, it's going to be 180 degrees. What if I were to add a lone pair? Yeah, that should cause the angle to be about 120. So this is probably not very likely because now my central atom has 2, 4, 6, 8, 10 electrons. So probably not very likely. But if I had that, what would the molecular geometry be? It would be bent, right? So it's labeled down here. The electron domain geometry is trigonal planar, but the molecular geometry is bent. So if I take out that triple bond and add a double bond, still the same thing. Triple bond, double bond, they're both still one electron domain, and they both still basically cause almost the same amount of repulsion. So technically these angles are not perfect here because a lone pair does not repel other groups to the same exact extent that a single bond does or a double bond does. They all have their own slightly different individual quantities of repulsion. So the actual angles will usually deviate a little bit from the standard 180 for linear, 120 for trigonal planar, 109.5 for tetrahedral. But they should be still relatively close, so that's reasonable to look at that. So these structures so far have all been linear, and I can rotate them out of the space, and I can see that. I'm sorry, not linear, planar. I can see that all the atoms in the lone pair are all in the same plane. Right, they're in the plane. They're in the plane of the paper. Once I go beyond 3 electron domains, if I add another electron domain, now I have a tetrahedral shape. So I can see there's no way to put all 4 of those groups in the same plane. I can rotate it and put 2 of the bonds roughly in the same plane. So I can put this here and this here roughly in the same plane. But then what I see is the other group, electron domain, which is the lone pair, is pointing away from me. How do I show that in 2 dimensions? How do I represent a 3-dimensional structure like this with bonds of 109 in 2 dimensions? It's hard to do. So usually if one of the groups is a lone pair, we usually put that at the top. So let me just swap this double bond out for a single bond. Oops. Because that's more realistic. Having a double bond would go beyond an octet. So most of the time, if I'm going to have a tetrahedral electron domain geometry, if I have a tetrahedral electron domain geometry and one of the electron domains has to be a lone pair, the term for this is trigonal pyramidal. And it looks like a pyramid. Right? So I've got the central atom at the top of the pyramid, and I've got these other 3 atoms kind of at the base of this pyramidal structure. Right? So the electron domain geometry is still tetrahedral because I've still got 4 electron domains. But when I'm looking at the molecular geometry, I know the lone pair is here, but when I'm looking at the molecular geometry, I just want to look at the shape created by the other atoms. So if my central atom has 3 atoms attached to it, it will always be trigonal. If those 3 atoms attached are at the base of a pyramid and the central atom is at the top of that pyramid, it's trigonal pyramidal. if I were to take the lone pair out, then what would the geometry be? It would still be trigonal because the central atom would still have 3 atoms attached to it. But without the lone pair repelling those 3 atoms, they pop up. Now everything is in the same plane. So now it's trigonal planar. Right? So visually, you might say, well, I mean, there's not much of a difference between them being in the same plane versus being at the bottom of a pyramid. But when we start to talk about polarity, you'll see there's a big difference for the molecules that look like this versus molecules that look like the pyramid. It creates a difference in their polarity, and it creates a difference for the properties of the molecule that result from that. So let's just look at a couple real molecules. So here's water. Right, so what do we see with water is it's not flat. I mean, the molecular geometry is flat, but the overall geometry of the molecule, if you consider where the lone pairs are, is not flat. The lone pairs are occupying space, and so the electron domain, I've got 4 of them. It would be 2 bonds and 2 lone pairs, electron domain geometry. Not there. It would be a tetrahedral. The molecular geometry would be bent, because the molecular geometry is just focusing on the atoms, and I have like 105 degree, 109 degree angle between these atoms.
I'm sorry, you said this was water?
Yeah.
1 hydrogen, 2 oxygens?
1 oxygen, 2 hydrogens. Right, so there's water. You can look at CO2. CO2 is linear, right, because there's only 2 electron domains. No lone pairs to push those electron domains into an angle. So when I have no lone pairs on my central atom, I just need to look at how many electron domains there are. If it's 2, it'll be linear. SO2, what's the difference between that and CO2? Well, the SO2 has a lone pair on the central atom. And so what that does is it creates an angle there of about 120 degrees. That's a result of the repulsion that lone pair creates for the bonded pairs. Right, but still, everything's in one plane. I need to get the 4 electron domains before it starts to become a 3-dimensional structure. Right, so when you're working on the lab molecules, what you want to do today in lab is for all the Lewis structures you drew, try to predict what the geometry should be first. Then get the model kit and see if you can connect the structures, the atoms together to give you the structure that looks correct 3-dimensionally, and I'll be around to check those out, make sure you're doing them correctly. BF3, no lone pairs on the central atom still. So that's flat or planar. All the atoms are in the same plane. And there are 3 atoms on the central atom, so it's trigonal planar. So that one we don't worry about because there's too many electrons around the central atom. But here's ammonia, NH3. What's the geometry? Trigonal pyramidal. Right, because I've got 3 atoms on the central atom, but they form a pyramid. It's subtle. It's not a dramatic pyramid. It's not like these 3 hydrogens are way at the bottom and this is at the top of a tall, skinny pyramid. It's kind of broad and flat, but it's still not totally flat because the lone pair creates a repulsion to these bonds and pushes them down. So as we'll see in a little while, this makes ammonia polar. If ammonia were flat, it wouldn't be polar. Because it's polar, it dissolves in water, it forms attractions, and that changes its properties dramatically. So we'll talk about that in more detail. So here's methane, CH4, the angles are all 109.5, so this is tetrahedral. Again, there's no lone pairs on my central atom, so the electron domain geometry is the same as the molecular geometry. Any questions about any of that? Okay, so hopefully that helps you kind of get a 3-dimensional visual. So you want to kind of keep a mental image of what those 3-dimensional structures look like in your mind. So when you're drawing them on paper, even though maybe you know the structure should be 3-dimensional, when you're drawing on paper, you can't really show a 3-dimensional structure well on paper. You can still see what it looks like in your mind, and you have an idea of what that shape actually is. And so here, some more examples the textbook shows. So if I have SO3, we talked about this one in terms of the Lewis structure last time. We said there are a couple formal charges here. And we said the resonance helps to stabilize those formal charges by spreading the negative out on all three oxygens instead of just on two oxygens. In terms of the shape, though, this Lewis structure does not do a good job of representing what the shape looks like. It looks like, it kind of looks like an upside-down T shape if I look at the shape that's created by connecting those atoms together. So when I draw my Lewis structure, when I start drawing it, I don't know what the shape is going to be. Right? We just said we can't analyze the geometry until after we have the Lewis structure drawn. So what you want to get into the habit of doing is, once you draw the Lewis structure the best you can, then you look at that central atom and you label its geometry. And you say there's 3 electron domains and no lone pairs, so that's trigonal planar. Then redraw the Lewis structure to show that shape. If you don't do this, you will probably incorrectly analyze polarity when it comes to that step. So it's important to redraw it to show what the actual shape is as best you can on the two-dimensional piece of paper, which is not hard to do for trigonal planar because the molecule's in that plane of the paper. So you want to have an idea of what these shapes are and represent the molecules appropriately. So this slide just explains what we already said, which is that the repulsion created by a lone pair is actually not exactly the same as the repulsion created by a bonded pair. And if you think about it, a bonded pair, the difference is the bonded pair has another atom at the end with a positive charge in its nucleus. And so that's not going to be as repulsive as an orbital with no positive charge at all. It's just completely occupied and populated by negatively charged electrons. So the negatively charged electrons that are here repel the bonded pairs a little bit more than the bonded pairs repel one another. So between the bonded pairs, we have an angle that's a little bit smaller than the expected ideal angle for a tetrahedral, which would be 109.5. So I'm not going to ask you questions about the actual angles, but you should be aware that they deviate a little bit from the expected 180 for a linear, or the expected 120 for a trigonal planar, or the expected 109.5 for a tetrahedral, due to the fact that sometimes, if I have more electrons in an area, that's going to cause a little bit more repulsion. So it's going to push these out at a slightly larger angle than it would if it were a single bond. So depending on the actual type of electron domain, it may repel a little bit more or less than other electron domains. All right, so let's look at a couple more examples. So here I get into a little bit more complicated molecule, and you'll see, obviously, some of the ones in the lab are a little bit more complicated, and some of the ones on the exam will be somewhat complicated. So the idea here is if I've got more than one central atom, I've got to analyze the geometry of each one. Right? So for this molecule, there is no label for the overall geometry of the entire molecule. I'm not asking you to label the geometry of an entire molecule. I'm asking you to label the geometry of an individual atom. So we have to do those independently. So I'm not trying to think about this as an entire thing. Shape is too complex. I just want to look at each atom. So I look at the carbon, count the electron domain, 4 of them. 1, 2, 3, 4. Just around the carbon, just focusing on the carbon. This hydrogen is not even in my mind right now. I'm just looking at the atoms attached to the carbon. Tetrahedral electron domain, no lone pairs, so it's also a tetrahedral molecular geometry. So I want to redraw that, because what I've got it drawn now, it doesn't look tetrahedral. It looks like the angles are 90 degrees. It looks flat, but it's not. It's tetrahedral. So I put the carbon here, and in my tetrahedral in my mind, I realize it's three-dimensional, and this one sometimes shown pointing away. So you use like a little bit of a dashed line to show that. To represent that, that'd be pointing back into the plane of the paper. The other hydrogen here might be coming out of the plane, so sometimes you see people use like a solid wedge there to indicate that's coming out at you. And then the other bond to the oxygen might still be in the same plane. And so in a tetrahedral structure, I can put 2 of my bonds in the same plane. The other 2 will be pointing in and out of the plane of the board. And I want to redraw it so that when we go to the next step, I'll be able to correctly analyze the polarity of that molecule. Then I still have another central atom. I still have one other atom that's connected to at least two atoms in the structure, so I need to look at its geometry. Independently of everything that's happening over here, I just look at the atom and the lone pairs and other atoms that are directly connected to it. So the oxygen has 4 electron domains, 2 lone pairs and 2 bonds. That means it's a tetrahedral electron domain geometry, but since only 2 of those are connected to atoms, that means it's going to be bent. Right? So the angles based on this tetrahedral electron domain geometry are going to be about 109. When I'm only looking at the atoms attached to the oxygen, I realize that 190-degree angle is going to cause its molecular geometry to be bent. Now I do want to put the lone pairs in there, though, because they're still part of the Lewis structure. So this and this are both Lewis structures. They're both correct if I just ask for a Lewis structure. But this structure down here is much better representing the actual shape of the molecule. If you made a model of this, which you'll be making models of similar compounds later, you'll see that if you try to draw it like that on paper, it actually looks pretty close to what the three-dimensional model looks like, and that gives you the best shot at correctly analyzing whether the molecule is polar or not. Another example here, even more complicated. This is one that you might have written for one of the lab formulas. So this one has 3 central atoms. I've got to analyze them one by one. So let me number these carbons so I can keep them straight. So carbon 1 has 4 electron domains. So I want to analyze the number of electron domains, the electron group geometry, and the molecular geometry. So the number of electron domains for carbon 1 is 4. That means its electron group geometry is tetrahedral. And since it has no lone pairs, the molecular geometry is also tetrahedral. So I want to redraw that carbon and show that only 2 of the bonds can be in the same plane. Do my best to represent the 109 degree angles that are there. Then I look at carbon 2. Carbon 2 has 1, 2, 3 electron domains. And so its electron group geometry is trigonal planar. And its molecular geometry then, because it has no lone pairs, is also trigonal planar. So that carbon can have all of the things bonded to it in the same plane and should have all the things bonded to it in the same plane. So I need to put a double bond to an oxygen on that carbon and a single bond to an oxygen. Doesn't matter whether I draw it like this or like this. No, it doesn't matter. Either way, the angles are about 120, which is what the molecule should have if it's trigonal planar. So I want to show that. Well, let me wait to put stuff on this other oxygen because it's still a central atom. Right, so I'm just looking at one atom at a time. So now I want to look at the oxygen here that I've recognized as a central atom. That oxygen has 4 electron domains. It's got a single bond, a lone pair, and another single bond. That's 4. So with 4 electron domains, the electron group geometry is tetrahedral, but only 2 of those are actually bonds, so I've only got 2 atoms attached to it. So if there's only 2 atoms attached to that oxygen, those 2 atoms attached are going to be bent at that 109 degree angle. So when I attach the hydrogen, I don't put it here because the oxygen's molecular geometry is not linear. I have to put it at an angle. So I could put it here. That's about a 109 degree angle. Or I could put it here, which is also about a 109 degree angle. Whatever is more convenient for me, it doesn't matter. Sometimes, and you'll find this as you're going through the lab molecules, sometimes when you draw it and try to draw it with the right shape, you'll find that it's easier to analyze the polarity of this molecule when the hydrogen is pointing this way rather than down here. It doesn't matter. Either way, it's the same molecule. So you can have it angled and pointing in whatever direction in space you want, as long as the angle is roughly what it should be in terms of whether it's 109, 120, or 180. Questions about that? So these are the molecular geometry labels that I would put on the exam question if it asked me for the molecular geometry for each central atom in that molecule.